Hi everyone, here are your Chapter 19 notes, which gets us into confidence intervals with proportions. So remember, we use confidence intervals to estimate the unknown population parameter. So we don't know what the true p or the true mu would be, so we need to come up with an interval that we think has a pretty good chance of capturing what we think the true proportion would be. And it uses a margin of error to create that interval. So remember, this is our formula for one proportion z intervals. So we've got our p hat right here. So given your sample, find the proportion within that sample, and that becomes your p hat. Your z crit, your z critical value, remember that comes from doing your inverse norm on your calculator or the reverse of your z table if that's what you prefer to use. Remember, if we're doing a 95% confidence interval, you need to figure out what this standard deviation would be away from the mean. So your upper and your lower tails are at 2.5%, right? So 0.025. Me personally, I'm lazy and I don't feel like doing the math, inverse norm, and I'll just do that left-hand tail and do 0.025 in my calculator, which is going to get me negative 1.96, and then I just make it positive. That doesn't bother me that it pops out negative. If you want to do the math and add the 2.5% to 95 and make it 97.5, you're more than welcome to do that. Not that hard of math to do, which would then give you the 1.96. That's up to you. If it were 90%, then your two tails would be 5 and 5. Right? So then I could do an inverse norm of 5%. And then if I was at, let's say, 80%, then my two tails would be 10 and 10. So then I could do an inverse norm of 10%. Right? So that's how we get our critical values. And then this looks very familiar to our standard deviation of proportions, but because it's not using the true p and the true q, we call that the standard error. Right, and that notation is SE with a subscript of p hat, right? Because we don't have p and we don't have q, so we're trying to create a confidence interval to estimate what we think it can be. So since we don't have the true p and the true q, the best we have is our p hat, which then gives us our q hat, okay? All right, so make sure we know how to interpret a confidence interval. We are blank percent confident that the true proportion of blank is between blank and blank. Make sure you can explain what confidence level is. So using this method many, many times, about blank percent of all possible intervals created will contain the true proportion of blank. Again, always add context. So your confidence level is kind of the success rate of the method that you're using. Only do this when asked, okay? Always, always, always interpret a confidence interval when you create one, but only explain confidence level when you're asked to do so. Don't do the extra work that's not necessary. Okay, so we did a confidence interval with our Hershey Kiss flips. So just quickly to get our brains wrapped around confidence level and width of the confidence interval itself. If I asked you to guess my age within 10 years, would you feel pretty confident about that? Yeah, probably. Within 5? Yeah, maybe a little less confident. Within 1 year? Yeah, probably a little less confident than you were at 5. So as I condense that margin of error, our confidence gets lower, right? So as the interval got smaller, did your confidence get bigger or smaller? It got smaller. How about catching a fly using a fly swatter? Pretty confident? I'm pretty good with those fly swatters. But what if I told you to catch a fly with chopsticks? How about toothpicks, right? So as we make that margin of error smaller and smaller, that vessel smaller, then our confidence goes down. So as your confidence level increases, as your confidence level increases, your interval will get wider. So as level decreases, your interval is going to get narrower. I have two W's in there, I just noticed that. Okay, all right, so we've got that. So as your confidence level increases, your interval will get wider. So increase, wider, decrease, narrower. So it may seem weird, but the confidence level is saying how sure you are that the true answer is held within those two numbers. So if you want to be more confident, right, we have to widen that interval. and vice versa. So you kind of find that perfect balance between the two. Okay, I have 10 million of these. So I could say I'm 99.9999% confident that tomorrow's high temp will be between 0 and 100 degrees. But is that very informative? Is that going to help people go out and say, what should I wear? No, it's not. Okay. So there we go. There needs to be a balance between confidence level and the width of the interval to make sure our interval is actually helpful and accurate. And don't forget that sample size plays a part in this as well. So when we do our conditions for making a confidence interval, again, check it every time. So these are very similar to our conditions of the sampling distribution problems that we've done in the past. I do have independence on there. That's kind of an assumption, not a condition, so we don't have to worry about that so much. But we do need to make sure we check that we have the random sample. So is our sample random? If not, is it representative of the whole entire population? We got to do the 10% condition that checks for independence, right? And then we have to do our success failure to check for normality. And in this case, it's a little bit different. Notice that it's not NP because we don't know the true P. It's going to be NP hat and Q hat, okay? So your conditions stay the same. It's just now when we do our success failure to check for normality, you're using your P hats and your Q hats. So not too crazy of a difference. Whenever you are asked to do a confidence interval, please panic every time. This is kind of an acronym to help you memorize the steps. So your P, identify your parameter of interest. So our parameters are either going to be P or mu. In this case, since we're doing proportions, it's going to be P. So P equals the true proportion of number of Hershey Kisses landing on the flat side, right? The A stands for assumptions/conditions, right? So sometimes we have to assume things when we check our conditions. And then N, make sure you always name the interval. Right now, the only interval we have in our tool belt is the 1 proportion Z interval, and always claim what confidence level you are going to use. I, calculate your interval, so actually do the math. And then C, write your conclusion. Make sure you always add context, okay? All right, so here's a problem we're going to work through about ghosts. So the May 2000 Gallup poll found that 38% of random sample of 1,012 adults said that they believe in ghosts. Find a 95% confidence interval for the true proportion of adults who believe in ghosts. All right, so let's go ahead and panic. So my first is P for panic, parameter. Just so happens that my parameter here is P. So P represents the true proportion of adults who believe in ghosts, because that's what we're going to try to estimate. Now we've got to check our conditions, so assumptions and conditions. So what's our first one? Our first one is random. Here is stated that they did a random sample. So stated SRS. Then we have to check our 10%. Well, I'd say that 1012 is less than 10% of all adults in the U.S. Of all adults in the U.S. I know. And checking conditions is a pain in the butt, but necessary. And then we have our normality, which in this case is success failure. So here we're checking to see if my distribution can be normal. So NP hat, so 1,012 times my P hat, which is 0.38. So 1012 times 0.38 is 384.56. That's greater than or equal to 10. And then NQ hat is 1012 times 0.2. Oh my gosh, I can't even do the math right now. 62. So that's going to get me, what? If I could type it in right. 688. I could just subtract that from 1012 too. Okay, so they're definitely both greater than or equal to 10, right? 3, put that 3 in there. So then we're going to write a statement just like we have in the past with conditions met. we can use the normal model to represent the sampling distribution. And then I'm going to specify what I'm going to use. I'm going to use the normal model. Use the normal model to represent the, and create, we got to specify what we're creating here, and create a 1 proportion Z interval with 95% confidence. Now, if this is a lot of writing, right? And if we're short on time, AP exam wise, you can eliminate, you can just stop. We can use the normal model, and you don't technically need to put that to represent the sampling distribution. That just kind of is going above and beyond. So make sure that you do specify you're using the normal model. Oops, I didn't write model. The normal model, and do specify that you're doing a 1 proportion Z interval with your level of confidence. Okay. All right. So I'm gonna go over here to the side again. So now let's actually do it. So we're using our normal model, right, to make a 1 proportion. So we got our P hat plus or minus Z crit times the square root of P hat Q hat over N. Okay, so my P hat is 0.38. We're doing 95, so that's 0.196 times 0.38 times 0.62 all over 10,012. Okay, so now, at this point in time, I would stop. I mean, I could technically do all that math out, but why do all that math when my calculator can do it for me? I'm going to show you how your calculator will do it for you. So if you have your calculator out, if you hit second vars, nope, that's not what I want. Stats, there we go. We haven't hit this stat button in a while. Okay, so remember with stat edit, that gets you into the list so you can make all your lists. Stat calc, what have we used so far? We used one variable, stats, right? But what we're going to be going over to is where all the tests. So this is all of semester 2 right here in a nutshell. We're going to be doing Z-test, T-test, 2 sample Z-test, 2 sample T-test, 1 proportion Z-test, 2 proportion Z-tests. But what you right now would be interested in is if you look at A, we're doing a 1 proportion Z interval. So if I click on that, it's going to say what my X is. Oh, well, so here, okay, here we're going to have to do some math. Since they gave us the percentage already, we're going to have to figure out what 38% of that is. So, oh, we already did, didn't we? That was my success, 0.38 times 1012. So I'm not sure if the I forget if the calculator likes decimals or not. I'm going to put it in and see what happens. 95% confidence, hit calculate. Yep, I didn't think so. So we're going to have to go in there and get rid of it. So A, there we go. So I'm going to round up to 385. It's not going to make that big of a difference. Hit calculate and hit enter. Oops, I lost it. I hit enter too many times. Come back, baby, come back. That's a song, right? Okay, so there is my confidence levels, or my confidence interval, right? So it gives us the P hat, it gives us our N. So we're at 0.35 to 0.41. So now I'm going to come back to this. 0.35 to 0.41, is that what I got? So 0.35, comma 0.41. Okay, so you could technically sit there and do all that math out if you want, but why do that when your calculator will do it for you? So I've did my P, we did our A for panic, I named the model and the interval that I'm using, right, with my confidence level. So there's my P and my A and my N. We just did our I right there. So now we have to do the C of panic, which is to write our conclusion. So write it in context. So we are 95% confident that the true proportion of adults who believe in ghosts, I guess in the US that believe in ghosts, believe in ghosts is between 0.35 and 0.41. Okay, so there we go. We just panicked a confidence interval. Okay, so state your parameter, state your conditions, your assumptions and your conditions, name the model, name the interval, show all your work for where the confidence interval came from, and right here, that's enough work. Show the formula, show the numbers plugged in, show your interval, and then interpret it in context. Alrighty? Okay, let's do another one. So an insurance company checks police records on 582 accidents selected at random and notes that teenagers were at the wheel in 91 of them. Construct and interpret a 95% confidence interval for the proportion of auto accidents that involve teenage drivers. Okay, so let's go ahead and start. My P is equal to the true proportion of auto accidents that involve teenage drivers. I'm trying to do this quickly. Our conditions, random, state it, SRS, 10%. I would say that 582 is less than or equal to 1/10 of all accidents. And success failure. And I've had people in the past write this in paragraph form, so if you want to write all of this like in sentences, have at it. I won't tell you no. So 582, and we said 91. So 91 out of the 582 is 0.516, I'm going to say, right, which is 91, so that's greater than or equal to 10. And then that would make my failures. So 582 times, so 582 minus 91 leaves us with 491. 491, which is greater than or equal to 10. What is that? 0.84. Okay, so with conditions met, we can use the normal model and create a 1 proportion Z interval. Okay. All right, so let's go over here and do it. If you haven't started doing it in your calculator yet, start doing that. So P hat plus or minus Z crit times P hat Q hat N. It's 0.16 plus or minus 1.96 times, and then you could even just use the ratios too instead of the 0.16 if you wanted to be really exact. We could do 91 over 582, then 91 over 582, and what was the other one? 491. Oops, I can't write small enough. 491 over 582, all over 582, right? If you wanted to do the proportions. So now when I go to my calculator, I'm going to type in, oh, no, don't restart. Stat tests A, 1 proportion, Z interval. So we were at 91 out of 582. So here we didn't have to do the math. It's going to do it for us. So 0.13 and 0.19. 0.13, 0.19. Got to remember that. 0.13, 0.19. 0.13, 0.19. So then we've got to write that conclusion. So we are 95% confident that the true proportion of accidents involving teens is between 0.13 and 0.19. Okay. All right. So let's do one more. Pete is running for class president and decides to poll some students to predict his chances of winning. He samples 100 students and calculates a 95% confidence interval for the proportions of students who will vote for him. He calculates this interval at 0.45 to 0.52. So what does this interval mean? Well, we would say that we're 95% confident, right, that the true proportions of students that would vote for Pete as president would be between 0.45 and 0.52, right? Okay. So is Pete going to win the election? I would say probably not. Why not? Well, if he gets only 45% of the vote, he's not going to win, right? So he has some values that are less than 50% in his interval. So I would say that there's probably a high likelihood that he's not going to win because there's a chance that he won't win within this interval. If all of those values in my interval were higher than 50%, then I would say he's got a pretty good chance of him actually winning, right? So for part B, how would raising the confidence level to 98% change this interval? It will widen it by a lot, right? And then for C, Pete wants to take another poll, but due to time constraints, only has time to sample 40 students. What would this change in the sample size? So if we reduce the sample size, wouldn't it make our confidence interval larger? It would, right? Making a smaller or a larger sample size reduces your variability, which is going to tighten up the confidence interval. Okay, so I think hopefully we are good to go with confidence intervals. Yeah, well, let's do this human cloning one because I think this is working us backwards a little bit. The Gallup poll is taken in order to measure the proportion of adults who approve of attempts to clone humans. What sample size is necessary to be within plus or minus 0.04 of the true proportion of adults who approve attempts to clone humans with a 95% confidence level? Okay, so now we're going to work a little bit backwards. Here we have to figure out what the sample size needs to be in order for my margin of error to be within 0.04. So we need to solve for n, right? So what we need to do is we need to think about what do I want to make my p hat? Okay, so for this type of problem, we don't know p hat, so we're going to end up using 0.5. Why do we use 0.5? Well, my face is in the way. Can I get my face out of here? There we go. If we made our p hat 0.1, then my p hat times my q hat is going to get me to 0.09. If I made my p hat 0.2, my p hat times my q hat is 0.16. At 0.3, I get 0.21. At 0.4, I get 0.24. At 0.5, I get 0.25. So we want the p hat that will give us the largest possible standard deviation and margin of error. That way we will know that our margin of error will be within it. Because if we pick something that's too small and there was an opportunity to make it larger, then we don't know that we're really at that number that we want. So when you pick the 0.5, that's going to ensure that we have the largest possible standard deviation and margin of error. So for this problem, to solve for n, we're going to make our p hat 0.5, right? But if we think about our formula, p hat plus or minus z crit times p hat q hat over n, what part is your margin of error? Well, right here, this is your margin of error, right? Your plus or minus. So I need that to be equal to 0.04. What is my z crit at 95%? 0.96 times my p hat q hat, we're doing 0.5 over n. Now we've got some math to do, guys. Isn't that exciting? So 0.04 divided by 1.96. gets me 0.020408. I'm going to try to have my calculator do as much work as it possibly can for me. I'm now going to square that answer, and I'm going to get some really crazy number. So I'm getting 4.1649 times 10 to the negative 1, a negative 4 I mean, is equal to the 0.25 over n. But I can just interchange that, right? So I'm going to do 0.25 divided by a second answer, which gets me 600.25, right? And now we got to decide, what am I going to do with that 0.25? Well, to ensure that I am within it, I'm going to round it up, right? So I'm going to round it to 601. So what sample size is necessary to be within the plus or minus 0.04? I would say 601 adults. Okay? All right, because there may be a few problems like that in Chapter 19 where you're going to have to find your N. Okay? All right. I think we already went through this. Okay, we're going to call that good. See you guys.